Okay, so yeah, welcome back. It's a great honor for me to be here on behalf of Harald's birthday. I think last time I was here probably was at the last big party for you. That was for your retirement party. I can't quite remember, but I don't think I've actually been here since then. And it was also then, of course, a fantastic event. So today I decided to talk about another continuation of what we did back then, and that kind of gels in nicely with what Anton started. In fact, Anton did most of the hard work for this presentation, so I just have to now continue along the lines. I'll talk about the problem of supergroup Chern-Simons theory. So for Anton, the group was a UN, and for me, it will be a sort of a supergroup, let's say SUN/M. I'll give you a very simple example of that type in a moment. This is based on work I'm actually finishing now with Nejla Agay, Asad Gainudinov, and Mikhail Pavelkiewicz, and there's also some ongoing work with a master student of mine, Taj McKnight, which I probably won't have time to talk about. So, and of course, it's based on the work that you've all heard about now from Anton with Anton and Harald. And of course, Anton had already told you much of the story, so that's the picture. Anton couldn't do good with pictures because that's my advantage now. I have all the pictures that go with Anton's talk. So this is actually the building where the ESI started. And so the inauguration of ESI was, I think, in April 1993. And I think this is precisely the day on which I met Harald for the first time, was probably this inauguration conference that we had somewhere outside Vienna. And then, yeah, we worked, both Anton and myself worked for 3-4 months as postdocs in this institute. For me, it was sort of, I was just finishing my PhD. I think I have to fly back from here to defend my PhD back in Hamburg. And then I remember how Harald one day came and said we should talk together, and we sat somewhere in, like over there in an office on the blackboard, and Anton was explaining Fogg-Rossley. And I think I was kind of pulled into this collaboration because of the unitarity aspects. I think that's why Harald felt like I should be part of that. And I think this is also why finally these papers become so hard to read, because until all this unitarity was implemented, I think this was a very technical type of calculations. But in the end, it worked. Now today, in fact, so I had an obsession with unitarity at the time, and today I kind of get rid of that, and we'll talk about super algebras, and I will have to give up unitarity from the very beginning. So there's a certain involvement here. So maybe give you first some motivation. So there's some motivation that has been around for a long, long time, even back in those days and in the early 90s. I mean, when you hear Chern-Simons, you think, of course, of the relation with Westermino-Witten models and with topological invariance, Witten's famous paper on the Jones polynomial. And of course, people immediately started to think about these things, also in the case of supergroups. So it's possible, of course, to define Westermino-Witten models where the affine algebra is not a bosonic, but a superalgebra. That has a very nice representation theory. Even Katz developed much of that early on. So you can also build Westermino-Witten models based on superalgebras. And then, of course, you can ask, so first of all, these Westermino-Witten models, in fact, at the time were not really constructed that many. In fact, it was much later when it was understood that it's related with holography, that people, and myself also invested more time in constructing these Westermino-Witten models. And I think that's a sign of what I talked about 15 years ago at your retirement conference. So these are interesting theories, these Westermino-Witten models based on supergroups, in particular because they're non-unitary. They're very nice examples of logarithmic conformal field theories, and they actually appear even in nature. So they appear when you have condensed matter systems of random disorder. Often their critical behavior is described by such models. So they're quite relevant to study, and there's a fair amount of material is known about that. And so, of course, it's then natural to ask, it's a natural impulse. I mean, what is the Chern-Simons description, let's say, of the space of conformal blocks of these things? Okay. Another line is, of course, again, Witten's paper on the Jones polynomial. We showed that from SU2 Chern-Simons theory, you can recover the Jones polynomial by computing anomalies along loops. Now you can try to do something similar with supergroups and kind of, if you can make it work somehow, to integrate holonomies along supergroups. And in fact, that was also done by Rosansky and Salur early on with GL11. It's the simplest supergroup, and we'll see that in a moment. And they argued that this had something to do with the Alexander polynomial, which is a famous, very basic invariant of knots and links. Their treatment, of course, sort of was heavily based on the Vestomino model and required some very strange regularizations of infinities. So up until quite recently, I was never even quite sure why they were so convinced that they had actually, except they matched it to the Alexander polynomial, of which one knew that it was. So then there's a sort of more recent application that kind of comes from the post-holography era. And okay, the interest, let's say, in n=4 super-Yang-Mills theory, which is this maximally supersymmetric gauge theory in 4 dimensions. It turns out if you put like an interface, so you take two of these n=4 super-Yang-Mills theories, maybe with different gauge groups, SUN gauge group on one side, SUM gauge group on the other side, and you separate them by an interface, and you make this interface also as supersymmetric as you can, then it's possible to kind of twist this theory and extract the topological sector, which turns out to be a supergroup Chern-Simons theory. Okay, so somehow at these interfaces in n=4 super-Yang-Mills, which is sort of probably the most interesting conformal field theories that people study these days. If you have an interface therein, somehow the supergroup Chern-Simons theory is naturally sitting inside these interfaces. And so that's was work in particular by Witten, Gayotto, Witten, Kapustin, Witten, Lina. When you then look at the literature, it actually turns out that very little is actually known about supergroup Chern-Simons theory. So even the question is, if you have a supergroup Chern-Simons theory, and the things that Anton also presented for ordinary bosonic groups, we know how to compute, for instance, the dimension of the state space, right? So this was related to this Verlinde formula. So what do we do with supergroup Chern-Simons theory? For instance, if we have a surface with some of higher genus with a number of punctures in there, what's actually the dimension of the space of ground states in this theory? That's a question that is not really, the answer to which is not really known and has not been. So maybe we keep this not as a guiding question behind. So in the purpose of this talk is to explain you that combinatorial quantization is ideally suited to answer this question. I'll show you sort of the algorithm by which you can actually compute these numbers, and of course, way more than just these numbers. These state spaces come equipped with a lot of interesting structure. Okay, so the main upshot of this is, as Anton already pointed, this combinatorial quantization has many interesting applications, and it's still, I think, a surprisingly powerful tool in answering modern questions in various regimes. We'll see a few other things coming up later. Okay, so here is the plan. So I will show you how to adapt this combinatorial quantization to the case with quantum supergroups, supergroup gauge groups. So we will define, as in Anton's talk, we will define for a surface of genus G and with n punctures and any supergroup G and some kind of parameter like the K, or I put it here in this Q that Harald reminded us, Q is e to the whatever 1 over K plus something. So there's this, the same parameter that Anton called K. It was a coupling of the Chern-Simons theory. Yeah, the dual Cox-Zeta number, which for the supergroup is often 0, so we can just forget. Anyway, so I'll construct a family of these algebras. I call them A. These are actually the observable algebras that Anton called A invariant. We'll see how to compute them, construct them, and then I'll explain a little bit how to do representation theory, and in particular, recover dimensions of spaces and other structures thereon. And if I have time, I will also talk about invariance of 3 manifolds. All right, and so of course, yeah, maybe. Okay, so here's the plan. I'll start with talking a little bit about the input. I mean, super algebras, I'll give you mostly one example of that. Then comes the second part. That's, I think, heavily relies on what Anton just explained. So I'll kind of go through that relatively quickly. And then in the final part, I'll talk about how to construct the states, how to build representations of mapping class group, and also hopefully show you a formula for invariance of three manifolds derived from here. Okay. Let's get started. So we are now post the quantization. So that we could start, of course, with the classical story. Then we would have some super manifold with something like the Goldman bracket, things like this. But so I'm already going one step further and want to construct straight this quantum algebra. So I already assume that the classical R matrix I've replaced by quantum R matrix, the group by quantum group, and I'll use that as a sort of the input in the construction. Okay, so a little past where Anton started. And so here the input is, so the technical term is a quasi-triangular factorizable ribbon super Hopf algebra G. And so for you, it's only important that it's some structure that provides us with a solution of Yang-Wechsler equation in R. And there's a little bit of extra structure. One has a ribbon element. You kind of saw that in Anton's talk somewhere when he computed the quantum trace. He didn't call it like that, but that was there. And you need some kind of integration theory. So that's the main ingredients that you need. And if you kind of fulfill all the right axioms, then you can start the construction, this combinatorial quantization. Now, I mentioned among Harald's friends, many people have gone through papers on Hopf algebras and have looked at pages and pages of axioms. So I could do this here too. So these are the pages and pages of axioms that one has to write in order to make this totally well defined. And of course, the main thing here is that it's super, so it's a graded algebra. It's a graded Hopf algebra, and there's all sorts of signs which make it even a little less pleasant to look through the axioms and to get it all right. But if you successful, you get the setup. So instead of going with you through all these axioms, lists of axioms, I will just show you one example. And that's the simplest example that you can imagine. It's actually surprising that such a simple example, which is simpler than UQSL2, but somehow has already a surprising amount of richness in terms of what you get out of it. This would be the example. So in general, I guess we would be GLNM, let's say. So the simplest case is GL11. Let's say you have a n equal 1. I mean, U1 gauge theory on both sides at the interface in the middle. That's where you realize this. Now, what does it look like? So I think most of you probably have seen the defining relations of UQSL2. And so the defining relations of this UQGL11 look as follows. There's two bosonic elements. These are just abelian generators. These are just commuting objects. And we choose now Q to be a p root of unity and P to be odd for all the axioms to be satisfied. And then we want these bosonic generators to be just the p power of them is 1. Okay, and then we add to this two E plus and E minus, and unlike in UQSL2, these are now fermionic. Okay, so that kind of makes them very infinitesimal. So they square to 0, and they satisfy these relations. You will remember, you kind of see, I mean, E plus minus commute. They are charged under Q plus minus, and then they satisfy this interesting relation between E plus and E minus. Okay. So again, if you have ever seen UQSL2 relations, this looks very familiar, but keep in mind this is way simpler because these guys here are fermionic, so they square to 0. So now what you can do is, also, then I told you that this is actually an example of a quasi-triangular factorizable ribbon super Hopf algebra. And I told you before what you need for that is you just need an R matrix. So here's an explicit formula for the R matrix, okay, universal element. You need a ribbon element. Here's an explicit formula. And you need a way to integrate elements. So here's an explicit formula. And then you go ahead and check that all the axioms are satisfied. And of course, you don't have to remember these formulas. Just know that. Yeah. On alpha, beta, you mean it only gives K alpha, not K? So alpha is just a name. K alpha is just a name for a generator. It's not a parameter. K1, K2. So K2 is indeed not there, yeah. So, right, so this K beta is, yeah. I mean, no, alpha is just a label. Okay. There's no alpha. I mean, it's just the commutator. So this K alpha is a little bit like the Cartan generator or this K element of UQSO2, and then on the top of that, there's another K beta in this theory, which this is because we are talking GL11 and not SL11. I mean, if I had SL11, we would get rid of this K beta. Okay, so then it would be really really the similar one. Okay, good. So now now I told you already that this is an interesting algebra, and let's see why it is interesting. So here you can do, I mean, even as an undergraduate student, you could do all beautiful exercises in representation theory of non-unitary or non-semi-simple algebras, and this is quite remarkable. So when you want to write down representations, because you have abelian generators and you have these fermionic generators, and the fermionic generator is squared to 1, there's a raising and lowering operator. So a typical representation would be a two-dimensional representation, right, where you have the eigenstates of K alpha and K beta, which are written here, and then raising and lowering, fermionic raising and lowering operators, okay? And that's the typical representation in terms of our everyday language, but also what mathematicians call typical representation. So it's an irreducible end representation that gives rise to projective modules, so you kind of have more of the mathy background. But what you then see is, and that's at the origin of much of the thing, is when you look at these relations, so the E minus, I guess, goes up here, and then E plus goes back here, but with a prefactor. And this prefactor, when E is equal to 0, then this prefactor vanishes, and so you can kind of go down, but you cannot go up again. And so this becomes an example of what is called an indecomposable representation, right, where you have a null vector, and you can build then, of course, these sub-representations, one-dimensional sub-representations where the fermions are trivial, which corresponds to E equals 0. And then you have some interesting representations which are four-dimensional, which have this diamond structure. And you can, for instance, find them very natural if you take two of these typical representations with opposite E eigenvalue, and you tensor them, you will find that you end up in an indecomposable representation that has dimension 4, right? Okay, 2 by 2 is 4, and it looks like this. And again, in the math terminology, again, it turns out that this is what's called a projective module, okay? So it is something that you cannot extend any further somehow. So you have these type of basic representations, and so the structure of representations is largely what makes superalgebras interesting, and of course also has to do with the fact that I alluded to before, that when you write, for instance, Westomino models on a supergroup, you get always logarithmic theories. That's because of. Now it will turn out that one important thing to understand representation is if you take your modular Hopf algebra or supermodular Hopf algebra, you can define an adjoint action on that, and I think Thomas asked about that before. So here's how this adjoint action is defined, including now the grading signs. And you can ask how the G as a module with respect to the adjoint action, how it decomposes into representations. And since you now know all the representations from the previous slide, it's just a matter of identifying the correct representations. And it turns out that this is the content. So there is a p squared minus 1 times this projective cover of the 0, so this diamond representation, and then a bunch of 4 representations, which are just these atypical ones. Okay, so this in this example, of course, is not much work. In general, in fact, this is a bit of work, and I don't know of any general theorem that gives the structure of this adjoint representation for an arbitrary quantum deformed supergroup. And so, as I will kind of tell you later, is so this is basically where all the work goes. And once you've done that work, you will be able to kind of compute all the data. Yeah. The S, also the S is the antipode. Antipode. So I mean, as I said, I kind of left out a few of the important objects, but yeah, antipode I didn't use, but it's a Hopf algebra. So this decomposition, again, if you decompose the left and right regular action, which is other actions on this Hopf algebra, in fact, it turns out it's a sum of only projective modules. This is much more canonical than this adjoint. So somehow in this adjoint is in some sense an more interesting representation in terms of. Okay. And of course, you can also do the tensor power of the adjoint, which will become just taking tensor power. Okay, so now you've seen one example of a modular super-Hopf algebra. Okay, and in some sense, I'm telling you, at least if you're interested in PSL and M, you've seen kind of everything that can happen in some sense. I mean, there's, of course, for PSL and M, you have wild representation theory, but these representations the others will not really enter the story in any case. So this is a very good example because it shows sort of much of the richness, and I think for the purpose of this talk, it will be sufficient to keep this example sort of in the back of your mind. Now, so this is the underlying, so this is what we need, what has to be given to us in order to start combinatorial quantization. And you know already from Anton's talk, it's mostly this R object to write down exchange relations. And so now we do more or less what Anton just told us to do. So first of all, we introduce a basic object, namely this quantum holonomy along a link. And I think Anton didn't really write this relation, but so here, I think, so here that's what he called A or B. I call it U. This is something like a holonomy along an open curve. And then we impose exchange relations of this type using this R matrix that is given for us with the basic structure. And it's possible to check that this admits two actions of the symmetry, of the gauge symmetry, which are gauge transformations acting in these two sites. And once you have this basic structure, which is sort of this local structure that you can then start to kind of glue it together according to the topology of your surface. So you're now taking yourself, sorry, I wanted to give you this one example. So if you do this, work this out explicitly, this is fairly abstract, but you have a very nice concrete algebra that you can write down. Again, it has two bosonic and two fermionic generators. The bosonic is called L alpha and L beta, and the fermionic psi plus minus. This algebra is different from the one I had before. It has two bosonic and two fermionic generators, but the relations are different. It's kind of more like the quantum group, the Hopf dual of the algebra I introduced previously. So it's a different non-commutative algebra that is in some sense, it's defined by these relations. So this is what this type of exchange relation can look like. Now again, according to philosophy that Anton described, what you do is you now marry this algebra with the topology of a surface. So you take your favorite Riemann surface with n punctures and of genus G, and now you draw like a graph on that thing according to the rules. You draw a graph and you put maybe some extra data like the ciliation that Anton explained. And then you write down an algebra generated by like these holonomies along all these different links. So all the topology is basically in this exchange relation between holonomies on different links. So when they kind of have nothing in common, they just commute, and otherwise they have these R relations that Anton also wrote. So there's a very nice way to define an algebra once you have this basic building block, the link algebra, and the choice of a graph. And so this defines a graph algebra. Again, Anton called this A, but it's coming from this algebraic quantum field theory community. I cannot call things that are not gauge invariant A, so I call it F. So this defines some kind of interesting algebra that somehow combines these local degrees of freedom, which are completely insensitive to, I just defined locally with the global features of the surface. And here, of course, the link to factorization algebras was already mentioned by Anton. Let me also say that this definition is, of course, made so that you have preserved all the gauge symmetry at these at the vertices. So there's an action of gauge transformations in each of these vertices, and the algebraic relations, the exchange relations are respect this gauge symmetry. Okay. So yeah, maybe I should briefly mention that, although it's so we talked about the link algebra. There's one other object that one could introduce. Anton also mentioned that briefly. You can also talk about the holonomy along a closed loop. Now this you can, of course, build. If you have a closed loop, you can just take 3 links like that, and you construct something that is gauge invariant here and there. So, and then you get a new algebraic object, which is sort of this holonomy along the closed loop, and you can derive the exchange relation for this object M, this monodromy, from the relations that I had given before. And so it turns out that these are the relations for this, what we call the time loop algebra. So this is not kind of a new object. Somehow it's sitting inside, very natural inside this graph algebra, and has an action of the adjoint action because there's only one set of gauge transformation that you can act on. And you can actually check that this is the same now. This algebra is the same as the symmetry algebra you started with. So you write down these exchange relations, and then you get these relations for our example of GL11, and then you go back to my slide at in the previous part, and you check that these exchange relations map one-to-one to the ones I wrote for G. So it turns out that this algebra of monodromies, of holonomies along closed loops, is actually the same as this supermodular Hopf algebra. And that's a more general statement. Okay, and then we come to the algebra of invariance, the observable algebra. Now, of course, the construction of this graph algebra depends very much on the graph, but as also Anton explained, now when you look at the algebra of invariance, the things that are gauge invariant, where things are put together in such a way that, that you build some gauge invariant object, and this object is actually much more canonical. It loses the dependence on the ciliation. It largely loses the dependence on the choice of the graph. Except this algebra here now depends really only on the genus of the surface and the number of plaquettes basically that you have on your. And so this is a nice way to associate an algebra to the combination. To the surface, given like a supermodular Hopf algebra. And I guess my main claim is it works. Modular Hopf algebras just as well. Works also for supermodular Hopf algebras. And so I should say maybe for mathematicians, supermodular Hopf algebra is actually not a modular Hopf algebra. There's a sort of two transparent objects, so that's why it's has to work a little bit to kind of. Okay, so now. So since the algebra of observable is not dependent really on the details of the graph, I think you can just define it in terms of the standard graph, which is a graph with a single vertex, and that's here. So I could write now relations of this thing with a single vertex. So you would have just one vertex, and then you would of course have like these things would all be loops. So you would have lots of copies of this monodromy algebra here. Now, of course, you can think of that also as a graph algebra for a generic graph where gauge invariance is imposed at all but one vertex. Okay, that's the easiest way to define what. And so Anton and I, so I think the first two papers, of course, we wrote together on this combinatorial description of the algebra, and then when we looked at representation theory, we decided to just work with the standard graph, and we did not develop a combinatorial representation theory, which in some sense, I think, was a tiny bit unfortunate because the combinatorial representation theory is actually now known as Kitaev lattice models. And if we had done this, so Kitaev lattice model starts sort of with the states, and it was defined, of course, 5 years later, 5 years after our paper. So that starts with states, and it turns out when G, this Hopf algebra, is a double, the Drinfeld double of some H, then you can actually define, first of all, like a spin model where you have 8 degrees of freedom sitting on the links, and then there's some operations in Kitaev paper, which is magnetic and electric triangle operators, and the product of these is this quantum holonomy. And so, so this is very natural. In fact, somehow in terms of the algebra of ground states and the gates, basically, our theory captured something that's even more general than Kitaev's model, because it's not only applicable to Drinfeld doubles, but even more generally for arbitrary Hopf algebras. But I think what convinced sort of people in the condensed matter why they paid much attention to that is that there was beginning a combinatorial description of a state space that was sort of the starting point. And so in some sense, when we generalize this now to the super case, it means that basically the spins can be sort of fermionic objects. So that's sort of a fermionic extension of Kitaev toric code. Okay, so that's just a little side comment. How am I doing on time, actually? Okay, I knew that I would save a lot of time because of Anton's brilliant explanations. Didn't lose you all. So back here, so we've defined this algebra, or family of algebras, AGN, depending on the genus and the number of punctures. And I basically told you that you can do that for any super modular Hopf algebra, and in particular for this GL11, UQ-GL11 is one example. And now, initially I said, of course, the main interest is now in doing sort of representation theory, understanding the structure of the state space, dimension of state space, maybe the structure on the state space. It comes as representation of the mapping class group. And so that's what I'll talk about in the final part. So, any questions? Maybe I should. Any questions on this so far? Yeah, that's a double of something. Yeah. So here you could apply this. So it might still be worth kind of working. Yeah. In view of time, maybe not, but I have a backup slide that explains a little bit more how you build these Kitaev. So the things, and you build this combinatorial description of some state space, and you have to implement, prepare the ground states, basically, right? And so you can do that with these operators and the ground state space, again, will then be identical to the representation spaces that Anton and I constructed in. Well, okay. Yeah, there is a Hamiltonian. So here, of course, here's just the state space of Chern-Simons. But in this combinatorial description of the state space with these spin chains, then there's Kitaev defined an operator, and basically the zero modes of that thing would be sort of the ground state space in which you can do your quantum gates and stuff like that. The spaces in the end are identical, but we didn't come from sort of a combinatorial description of the state space. The combinatorial description of the algebra, and then did representation theory in a non-combinatorial way. So it was I guess, a mistake that probably is due to the fact that Harald had left. Okay, so anyway, so in terms of physics, of course, or results, it's identical. But yeah, so right, so she noticed, of course. She kind of noticed and worked out how precisely this relation goes. If you want, I have slides later. Okay, so we want to do representation theory, construct sort of these state spaces. Again, the guiding question in the beginning was, how do we actually compute now the space of ground states, or the space of conformal blocks associated to this supergroup Chern-Simons theories? And what does the action of mapping class group look like on this? And so now we follow the recipe that more or less that we had developed also before. So now I have to slow down a bit because this is a part that Anton didn't cover. So it turns out that you can actually build representations of this graph algebra for the standard graph, and hence also for the observable algebra, on the following thing. So you pick, now you have to mark or label all your vertical Wilson lines, and we're going to label them by irreducible representations of our algebra, pi 1 to pi n. And then for each genus, we're actually going to add in one copy of this G-add module, which is a module of the underlying modular supermodular Hopf algebra. So we consider this tensor product of representations of G. So it's a representation of G, but the main claim now is that so the main claim now is that that this space also carries an action of this algebra of Chern-Simons observables. Okay, so you can define on this space an algebra, a representation, an action of this algebra of Chern-Simons observables that we just defined before. And that's why this is a theorem. It turns out that that this action of the Chern-Simons observable centralizes the canonical action of the Hopf algebra. So, so in some sense, it's a little bit similar to the relation between like SUN representation theory and permutation group theory. It's not quite not a full analogy, because in this case it's not double commutant, but in order to understand a lot about representation theory of SUN, you need the representation theory of permutation group, and here it's a little bit similar. Turns out if you want to know about the representation theory of these observable algebras, in some sense, you need to know mostly the representation theory of G, which is what we worked for in the beginning. Okay, and so this is something you can prove, and that provides now complete control, like in this example of permutation group versus SUN, complete control over the representation theory of these observable algebras. But it turns also out, I mean, of course, that makes these representation theory of observable algebras as intricate as the representation theory of G. So all these things with indecomposable representation that I showed you for GL11, they will also appear now for these type of observable algebras. So in particular, you can build representation spaces W. You take this representation space here, and you look at the subspace of G invariance in there. That will give a representation of your algebra of observables, but typically will be an indecomposable representation. Now, okay, before we look at this in the example of GL11, let me maybe go one step further and look at particular observables. These are these sort of Dehn-twist observables. So if you have a closed curve, it's also like an Anton stock, a closed curve on your graph, you can take the product of these monodromies or holonomies, that's this ABC that Anton had, and you can then take a certain functional thereon that was Anton's quantum trace. Now the quantum trace somehow in this naive way doesn't work for superalgebras because it's too degenerate. So that's why you have to work a little bit to come up with a sort of smarter formula, and that smarter formula is this. That involves now the ribbon element, this right integral that I had said was part of the structure. And when you do this right, then you get a nice set of objects, which are sort of the non-semi-simple extensions of these things that Anton had on the blackboard here when he introduced these quantum traces. And so for each curve, you have, of course, associated a Dehn twist, which is obtained by just cutting the surface along the closed curve and then rotating by 2 pi and gluing it back in. And so it turns out that these elements here, which are now elements in the algebra of observables, these are particular observables of the theory, they satisfy up to some projective phases the same relations as the generators of the Dehn twist of your surface. Okay, so in that way you obtain through these, so there's particular observables in this algebra which just satisfy the relations of the mapping class group. So Dehn twist generate the mapping class group of the surface, and all the relations are right. So you get the representations of the mapping class group. And now let's see how that works out in this one example, just to see that you have the tools at hand now. So let's say if we do this one example, we take the torus, no puncture, just the torus. Then I told you that the state space Wait, maybe let's go back quickly here. The state space, so there's no punctures, so this will be there, and this is genus 1. We have just the one G at there. Okay, that's the space V. And that space G at we computed before. This was the formula I told you about like many slides back when I said this is sort of the most maybe non-trivial statement that you need about this thing. So this would be G at is given by this decomposition. So it had P squared minus 1 times this projective cover of P0. I changed notation slightly here, but and then these guys here. And so what you now see is if you look at the invariance in there, there's an invariant sitting in each of these projective covers. At the bottom of this thing, there's an invariant, but there's some other invariants which sit here. They're just irreducible summons. And so in total, you have a dimension of your space is P squared plus 1, okay? And the intricacy of the representation theory now means that somehow the algebra of observables in this case for the torus will have an indecomposable representation which has a block decomposition into something that is P squared minus 1 coming from here and then a two-dimensional other piece. Okay? And so you can now go ahead and work out the interest generators, which is in this case just a modular group, and you would obtain a representation of the modular group. I mean, this famous S and T with all the relations. And this is just following now the recipes. You just plug it into the formulas. Okay, we had to work a little bit with the quantum trace to upgrade that to this case to make it sufficiently non-degenerate. And then you can work out, you can introduce a basis of this P squared plus 1 dimensional space, and then work out explicitly just doing standard commutation relations using these exchange relations that we've given before to work out the action of S and T generators, the modular transformations on this space. And this action, in fact, it was related to something Mikhailov just a few years ago worked out, but he didn't really understand very well what the state space was. So it needs a lot of interpretation in his formulas. So that's one of the very simple first things that you can get from this, just applying this formalism and just using these exchange relations and the proper definitions. You get a representation of this of the modular group that is P squared plus 1 dimensional. So in fact, you get lots of representation of the modular group, and that's what it looks like. So I'm running out of time. Let me just very briefly talk about free manifold invariance. Can be obtained now by doing Hegardt decompositions of the free manifold, which means you take the free manifold and glue it from two handle bodies, and you kind of, before you glue it, you apply a mapping class group element to make the gluing. And then there's a formula that we propose that allows to compute this free manifold invariant from, so the main ingredient, of course, is this mapping class group element associated to this, the representation of the mapping class group element associated to this row that you use in the Hegardt splitting. This is, again, a concrete formula that you can work out. So you start with some state in your state space and this V invariant, which is given here. You apply this element of the algebra, this particular observable, and again, everything follows from just, you can do all your computation using commutation relation. You apply the functional, which is just the g-fold power of this integral. You have to compute some particular normalization, which is given here. And the claim is that then gives the free manifold invariant. And indeed, we've checked that when G is semi-simple, even with trivial grading or non-semi-simple, you recover known free manifold invariance. And in this case, you also, for length spaces and UQGL11, you do recover the Alexander polynomial in a way that does not require any regularization of learned results. Okay, so that brings me to the end of this presentation. What I was mostly trying to show you that this combinatorial quantization in the context of this Chern-Simons supergroup Chern-Simons theory provides a very powerful, efficient algebraic tools to actually compute all the data that you want. So you have to do a few upgrades, basically, of the previous construction to account for non-semi-simplicity and the grading signs. But after that, you can more or less use this machinery to compute everything, and this is very, very explicit, not only for GL11, where you can, of course, easily now go to higher genus and things that I didn't show you, but you can also apply this to other supergroups, and it's going to be sort of the same. The machinery always works, and of course, the results will be in which supergroup you use. Applications, I said, include invariance of nodes in 3 manifolds. I alluded to this. I didn't really spend much time on it, but in some sense, this is equivalent to just computing a space of ground states in these Kitaev lattice models or Levin-Venn ring networks models. And so the extension to grading means that we can now admit for fermionic systems. Finally, of course, just remind you that this is related to calculating the state spaces sort of in the interfaces of anything for Supergroup theory. And essentially, all you need in terms of to start this construction is a good decomposition of this adjoint representation. From my point of view, sort of the main open problem that at the moment I only know to address case by case. One could do better than that. That brings me to the end. Happy birthday, Harald. So I recycled this slide actually from the previous, from the 60s. I had an extra happy retirement. Now it's a happy birthday slide, as it was meant to be. And I would say, I was looking yesterday, in fact, for some photos from the old days. And of course, from the old days, these are still paper photos, so it's very painful to look for photos. And I also didn't really find that many, actually, none that was showing you at the time. But I think somehow I feel that things haven't even, in some sense, not changed that much, especially when I look at you. You look, for me, still the same. And also when I come, now staying in this Kaiser Franz Josef Hotel, and the lobby is exactly the same, but somehow the interior is quite refurbished. So that's where I started also here. I stayed there the first few months when I was here. And I think maybe this is something that Vienna is particularly good at, kind of to keep on the surface look like the same, and then internally refurbish and modernize. And I think you are probably a perfect example of that yourself. So in this sense, I wish you happy ongoing retirement and many, many years to come.